You ever just stop and think about what's actually happening when you flick on a light switch? I mean, we do it all the time, right? We totally take it for granted. But inside that little wire, well, there's this entire invisible universe that powers our world. So let's journey inside.
Yeah, this is something we do a dozen times a day. Probably more. You complete a circuit, a bulb glows, and we just don't give it a second thought. It's kind of like simple everyday magic, isn't it?
But of course, it's not magic. It's it's this huge, chaotic, and unbelievably fast-paced drama, all playing out at an atomic scale. So, what is really going on inside that tiny metal wire to make the light just turn on? All right, to answer that, we've got to meet the main characters in this story. You know, the invisible agents who are responsible for carrying all that energy from the switch to the bulb. So say hello to the free electron. Now, in certain materials, especially metals, you've got these outermost electrons that aren't really tied down to their atoms. Think of them like a restless crowd, just free to wander all over the place. And these tiny little drifters, they are the absolute key to everything. And this right here, this is exactly why some materials act so differently. Conductors, like the copper in our wires, they're just jam-packed with these free electrons, totally ready to move. But then you have insulators, like the rubber coating on that same wire. In those, the electrons are completely locked down. And that's why they don't conduct electricity and, why they keep us safe.
Okay, so we've got these carriers, right? These free electrons, but how do they actually move? Well, probably the best way to wrap your head around it is to imagine a river. So when these free electrons are nudged to move in a specific direction, that flow, that's what we call an electric current. And it's really important to get this. It's not about one single electron racing from the start to the finish line. Nope. It's about the collective movement, this big shuffle, just like water molecules in a river. And we measure this flow in amperes, or, amps for short.
And look, the core idea here is really simple. Just like you see water flowing from a high-pressure tank to a low-pressure one, electrons do the same thing. They flow from an area where there's a bunch of them, a surplus, to an area where there's a deficit. The principle is exactly the same. Things just naturally move from a place of high concentration to a place of low concentration. Makes sense, right?
But the scale of this flow, it's mind-boggling. Get this. A single amp of current, which is about what a regular light bulb uses, means that more than 6 quintillion electrons are flowing past any single point in that wire, every single second. That is an unimaginably huge river of charge.
Okay, so we have this river of electrons. We've established that. But rivers don't just flow on their own, do they? They need a gradient, a slope, a difference in height to get going. So what's the electrical version of that slope? What's giving it the push? Well, that push is called potential difference, but you almost certainly know it by its much more common name, voltage. That's it. It's the electrical pressure that forces those electrons to get a move on from one point to another. It's super simple. No voltage, no push. No push, no current. And this whole idea of a difference causing something to flow, it's literally everywhere in nature. It's the reason water flows downhill. It's why heat moves from your hot coffee cup into the cold air. It's why a ball falls to the ground. In electricity, the flow is just from a high electrical potential to a low one. And it's all thanks to voltage. Now, here's something that, I gotta admit, trips a lot of people up. So let's just clear it up right now. The actual flow of electrons, what we call electronic current, goes from the negative terminal to the positive one. But for historical reasons, way before we even knew electrons existed, scientists kind of just decided that current flowed from positive to negative. We call that conventional current, and believe it or not, it's still the standard we use in circuit diagrams today. So yeah, they're opposite, but they're both describing the exact same thing. Okay, so we've got the flow, that's the current, and we've got the push, that's the voltage. But the journey for these electrons is not a smooth ride, not at all. They face this constant obstacle, a kind of inner friction. So picture this. Without any voltage, no push, the free electrons inside a wire are in total chaos. They're just zipping and ricocheting around randomly in every possible direction, constantly bumping into each other and the metal atoms. So there's a ton of movement for sure, but there's no overall progress in any single direction. It's just a big random mess. But then we apply a voltage. We give them that push. No, don't get me wrong, they're still bumping into everything like crazy. But now Now there's this slow, overall drift in one direction. And it's this constant pinball machine of collisions with the atoms in the wire that creates an opposition to the flow. And that obstruction, that opposition, it has a name: resistance. It's basically the electrical friction that every current has to fight against. In a material like copper, the resistance is super low, but in the tiny filament of a light bulb, it's really, really high. And here's the cool part. That friction is actually the whole point. It's what turns the electrical energy into the light and heat that we actually want. And here is where it all comes together. The push, the flow, and the friction. Voltage, current, and resistance. They are all beautifully linked by one simple, elegant, and super powerful formula: Ohm's law. This is one of the fundamental rules that governs, well, almost every simple circuit we use every day. So, there you have it. We've met our key players: voltage, current, and resistance. Now let's go all the way back to that simple light switch from the beginning and see how this whole team works together. Okay, here it is again. But now we can see it with totally new eyes, right? The cell, or battery, that's providing the voltage, the push. The wires, well, they're the path. The switch is our control, opening or closing that path. And the bulb, that's our big obstacle. That's what's providing the resistance. All right, let's walk through the action, step by step. First, the battery creates the voltage. Then, you flick the switch, closing it, and completing the path. That voltage then pushes the current, our river of electrons, all the way through the circuit. Now, as that current fights its way through the high resistance of the bulb's filament, all that friction generates so much heat that it literally glows. And bam, we get light. See? Every single part has a job to do. And you know, maybe the most fundamental rule of all is right here. For any of this to work, the circuit has to be a complete closed loop. If there's a break anywhere, anywhere, an open switch, a cut wire, that river of electrons has nowhere to go, and everything just stops. Instantly. So there you have it. We've uncovered the amazing world inside the wire, at least for a simple battery circuit. It's a steady, one-way flow that we call direct current, or DC. But the electricity in our homes, that's a whole different beast. It doesn't just flow in one direction. It actually vibrates back and forth, 50 or 60 times a second. So that leaves us with one final question, doesn't it? Why? What makes that alternating current in our walls so special? Well, that's a story for another explainer.